Good morning, everyone. Thank you for showing up for Science Sunday. This is the second lecture of a planned 19 if you count the introduction, which was a couple weeks ago. I appreciate it. I know some of you have come from different places. Many of you aren't accustomed to being in a place like this. I particularly enjoy that this congregation of this Unitarian church is very welcoming to those of us who have a naturalistic philosophy and a scientific worldview. I don't subscribe to any kinds of philosophies or beliefs that entail supernaturalism, and many of the congregation here do not as well. And this is a Unitarian church is very welcoming to those like me, and perhaps like some of you. All right, without further ado, this is the second program in Science Sunday. I talked the first time about the Big Bang, and then had also an introductory lecture about why scientific education is important. And I'm going to address a couple of topics from each of those today. So, where do stars come from? The lives of stars and the story of gold. What does gold have to do with stars? I got that question about 2 days ago. I was playing some board games, as it happens to be, with a good friend of mine, and told him what I was going to be talking about. Then he said, what does gold have to do with stars? Well, if any of you happen to have that same question, perhaps by the end of today, you'll have an answer to that. Where do stars come from? So, as I said in the introductory lecture about the Big Bang, the idea that the stars are other suns was not proved definitively until the late 1800s. And that's relatively recent in the span of human history. So, what are suns? What are stars? What causes them to shine? Some of you may recall the story of William Paley, who tried to figure out the age of the universe by using scriptures in the Christian Bible, and he came up with a particular date. I don't remember it off the top of my head, but it was a very specific date, about 6,000 years ago. And that was done in I think the 1700s. And then about the 1800s, when the scientific revolution really got underway, people like Lord Kelvin and James Clerk Maxwell, etc., started exploring thermodynamics and where light comes from, etc. And they had some initial thoughts about, well, maybe the sun is chemical energy. Maybe it's burning things just like a fire. And that's quite reasonable. You can expect that our ancestors also believed that the sun was a giant fire. If it was a giant fire, who was fueling it? Maybe it was rekindled every morning. So you had to invent the idea of somebody who comes along to rekindle the fire. One of the videos I showed at the introductory lecture during our Humanists meeting 2 weeks ago had, was it Bill O'Reilly, who said something like, the sun, where does the sun come from? Who put that there? Can you explain that to me? Well, I hope so. But it's a reasonable question. The question isn't bad. It's just that he hasn't encountered the answers so far, it seems. So where does the sun come from? Is there somebody in a golden chariot who rekindles the fires of life every morning? Well, again, about the 1800s, when we had some moderately sophisticated scientific theories, we thought maybe the sun burned. And then they discovered thermodynamics and that a compressed gas, as gas compresses, it heats up. So maybe the light of the sun had to do with bleeding off energy from being compressed into a star. And Lord Kelvin did some calculations about that and came up with an estimate that the sun must live for a few million years, which was much better than William Paley's estimate. But there was a problem. Some of you may have heard of a chap named Charles Darwin. So Charles Darwin had this idea about the way life arose and progressed through the ages and evolved, right? Natural selection. Well, old Chuck, as I like to call him, his idea was predicated on the notion that there was a vast amount of time. Well, when Lord Kelvin came up with a very scientifically rigorous, mathematically sound calculation about how old the sun was, it wasn't nearly old enough to allow for evolution to have occurred. So Charles Darwin, in a sense, predicted that the sun, whatever is driving the sun, whatever keeps it alive and makes life on Earth possible, must be hundreds of millions or perhaps even billions of years worth of energy stored up in the sun. But nobody knew how that could possibly happen. But his theory of natural selection and the way things happened on Earth and the geologic record to a certain extent at that time, as known, both implied that the sun had been working for billions of years. So how does that happen? We're going to talk about that today. So this is a picture of some actual stars. This is not computer generated. One thing you'll notice is that stars have different colors. There's red ones and white ones and blue ones and gold ones. There's some colors you don't see. You don't see purple. You don't see green. All right? Why is that? Well, it's largely because of what constitutes these particular stars. This is a wonderful mix of many splendorous colored stars. Where do they come from? Well, remember last time we talked about the Big Bang. This is an image of the cosmic microwave background radiation, which is the farthest light and the oldest light that we can receive here on Earth. And this light is left over from the time when the Big Bang became transparent to light. So you'll notice that there's some little bit of clumps. I remembered my laser pointer today. So you get these little clumps in this over here. So I talked about that during the Big Bang, where those clumps may come from. But the important point is that the clumpiness that resulted a few 100,000 years after the Big Bang was initiated, those clumps are what provided the centers for gravitational nucleation. That provided a dense gravitational nucleus around which other gases, primordial gases, there was really no dust at that point, around which gases collapsed to make the first stars. And also, as we talked about in the Big Bang lecture, the universe at this time comprised hydrogen and helium and a tiny bit of lithium. No gold, no carbon, no oxygen, just hydrogen. So where does all the other stuff come from? We're going to talk about that. Here's a picture of a stellar embryo. This is a picture of the Orion Nebula. I've talked about that in other discussions. Looks a little washed out, but this is a star factory or a star nursery. There are new baby stars being born in this location, even as we talk, as we meet here today. And this is a collapsing cloud of dust and gas. It is because it exists today during our time rather than 14 billion years ago, there is dust. There's dust that has other chemicals in it. It has carbon and whatnot. Well, maybe that explains why there are other elements. Maybe they just have been generated by empty space, carbon and oxygen and gold. Maybe those have just been generated by some mystical property of empty space, and they happen to be present in this stellar nursery. This is a zoomed in view of Orion, and these little blobs in here, these are actually baby cocoons for stars. So each one of these little blobs is a star and perhaps a solar system or an alien solar system that is being formed. Here's a close-up of what one of those looks like. You see it's a little disc, a little flattened there. Well, again, that is a real picture of a baby solar system. And you see this tiny little glow in here. I can't hold my hand steady enough, but there's a tiny little glow in there. That's because all the gas and dust in that disc is shrouding the light of a newborn star. So we have, if we look out into space, we see stars that are young, we see stars that are just being born, we see stars that are well on their journey to just emitting light and being what we would call a steady state, like our sun. So we see stars in various stages of formation, or after they have, in some sense, died, after they've stopped using nuclear energy. Here's another image. This is an artist's impression based upon scientific data of what a really close-up view of that particular baby star might look like, including the idea that there are these jets of particles and gas that are emitted from the poles of the star, so it's spinning this way. And this gas and dust that's in here will eventually likely become some sort of planets. So this is what stars come from. They come from gas and dust that is pulled together by gravity, and it has a fairly interesting birth process. Here's a typical scientific diagram. It's called a Hertzsprung-Russell diagram after the scientist who came up with it. This is luminosity or brightness, and then this is temperature. So from looking at things that are hot, you know that as things get hot, they go from a dull red to a bright red to yellow to white hot. And if you get them absolutely hot enough, they become blue hot. So that's what this color spectrum is about, the surface temperature of the star. These stars are actually hotter, have a hotter surface temperature than these. And then this is the luminosity, the total light output. You see that there are some stars called white dwarfs that are white hot, but they don't have a huge amount of luminosity. You also have some red stars that have a very great luminosity. They're incredibly bright, but they're not particularly hot. They're red. The interesting thing about this diagram is that this doesn't just represent one star during its entire life cycle, but it represents the entire life cycle possibilities for a given star. So this little yellow star represented here is about the kind of star that we have with the sun. And over time, I'll get to that in a moment, and this is another representation of the kinds of stars and the relative numbers of stars that we see. If we just pick a spot in the universe, how many red or orange stars will we see? How many yellow stars, like our sun? Our sun would be one of these. How many blue, bright stars would we see? And how many superluminous blue stars would we see? So this gives an idea of the relative abundance of stars. And one of the things you see from this is that the most common types of stars are small and red. And that doesn't happen to be the kind of star that we have, but they're quite common. But because they're so small and because they're dim, they have lower brightness, they're harder to see. So it's harder to find these stars, but when we look nearby in astronomical terms, within 100 light years or a couple hundred light years of our location in the galaxy, we see that most of the stars that are within that 100 to 200 light year bubble near us are comprised of these red, dim, small stars. So I talked about how the Hertzsprung-Russell diagram is not just a diagram about a particular star, or how different stars exist in the whole frequency or distribution of stars. It can also talk about the life cycle of a star. So during our sun's lifetime, it will follow this blue trail. So it starts off here, and again, this is about color and brightness, so it becomes redder, but brighter. And then something interesting happens. There's something called a helium flash. We'll talk a little bit about that. And then it gets even hotter. Remember, this is warmer or hotter temperatures. So it gets hotter, and then it gets redder again, and gets even brighter until something happens here. And then whatever happens here, and we'll talk about this, leads, if I trace this line throughout the whole life cycle of our sun, it would plummet down into this area here. It would become a white dwarf. And we're going to talk about why that happens. The helium flash is where instead of burning hydrogen, and I'll talk about hydrogen burning in a moment, it rapidly burns a shell of helium that has built up around the center or the core of our sun. So regarding helium flashes, this is a time-lapse photograph of an actual helium flash. This is Monocertes M838, I think. And it shows in May of 2002, there was a light bubble, there was a flash of light that came out of this star because it rapidly and fairly explosively burned helium. And that flash of light has illuminated more gas and dust around the star over time. This is not an expanding envelope or a cloud of gas and dust. It's not like the gas and dust itself is going like this. This is the light that came out of that helium flash, super bright pulse of light, is moving out at nearly the speed of light, essentially the speed of light, and illuminating more and more of the surrounding gas and dust over time. And they have actually made movies of this as well. So from 2002 to, what is this, 2004? So just 2 years here, it went from this bright little compact illumination. So this is 2 years later, or 2 light years further illumination around this star. Beautiful object in the space. In fact, some of the most beautiful things we see in space are due specifically to the life cycle and life processes of stars. So again, that's the helium flash. So let's talk about the kinds of stars. So here's a depiction of planets in our solar system. It's got Mercury, Mars, Venus, and Earth. You'll see that Mars is relatively small compared to the Earth. And then here's the Earth, and here's some of the giant planets, Neptune, Uranus, Saturn, and Jupiter. And then here's Jupiter compared to, I believe this is our sun right here. So remember I was talking about those very common, dim, small red stars? That's kind of what these dim red stars look like. They're not much bigger than Jupiter, a lot smaller, a lot less bright than our sun. So here's our sun, here's Jupiter, here's some of those common red stars, and here is, I believe, the star Sirius. The rest of them are just kidding. The name Sirius, that happens to be the star that looks the brightest to us because it happens to be a bright star and it's relatively closer to us than many other stars in the sky. So to us, in the sky, it looks like the brightest star. It's a winter star. Well, here's that same star, Sirius, and you see how it is compared to some other stars. You've heard perhaps of the stars Castor and Pollux. Here's the star Pollux. Here's Arcturus. Here's Aldebaran. So this giant star, which is, look, it's about twice the size of the sun, maybe 3 times bigger, is a tiny little dot compared to this star. And this star is down here. And Betelgeuse, a star in the constellation Orion, is vastly larger than this star. And the largest star we know about, actually there's one that's been discovered that might be a little bigger than this. There's some debate about it. What's that? YV Canis Major? Is that what it says there? So this star, compared to Betelgeuse is just a softball to a basketball compared to that thing. So imagine the difference between the size of this and the size of our sun. And one way to think about this is if our sun were the size of a softball, if you could hold it in your hand like a softball, then this star would be 100 meters larger, much larger than this building, right? So stars can range vastly in terms of size and in terms of temperature and in terms of color. So what does it mean? What do these colors have to do with anything? Do any of these stars emit gold? Well, what do the chemical elements have to do with stars at all? I've talked about hydrogen. I've talked about a helium flash. What's that have to do with other chemicals? So there's a process that happens that was discovered in the 20s by Arthur Eddington. Soon after Einstein came up with E equals mc squared, and that implied that you could get energy from operating on mass. What? Oh, okay. So Arthur Eddington, soon after Einstein came up with his theory of relativity, said, well, maybe this process of converting mass into energy is relevant to what happens in stars. So for the first time in the thousands of years of human history, there was an idea that was a plausible explanation about how stars generated their energy. And because, remember that E equals mc squared, so c is the speed of light, and when you square it, it turns into a huge number. The implication of that is from a tiny amount of mass, you can get a vast amount of energy. Well, for the first time in human history, we had a plausible explanation about how stars could get energy out of reactions involving mass. And it was also plausible that these processes could last for billions of years. So a prediction that Charles Darwin made, even though he didn't make it explicitly, he didn't write it down about our sun, an implicit prediction that Charles Darwin made about the fact that our sun must have lived for billions of years was proved to be correct when we discovered that you could convert mass into energy. And that's what happens. And then in 1957, the most famous paper about how these different processes occur came from a husband and wife team, Margaret Burbidge and Geoffrey Burbidge. Margaret is still alive. She's working in California. And William Fowler and Fred Hoyle. William Fowler won the Nobel Prize for his contribution to this. The Nobel Prize can only be given out, is it 2 or 3 people? 3 people. So a couple of people won the Nobel Prize for their work on the nuclear processes in stars, and he was one of them. And then Fred Hoyle, who was a famous cosmologist and physicist studying the stars. Notably, Fred Hoyle was, throughout his life, an advocate for something called the steady state theory. He did not subscribe to the theory of the Big Bang. Of course, he didn't live long enough to see some of the evidence build up that we went through during our last talk. But these people came up with a whole series of nuclear processes that could explain what happens in stars. And it starts with hydrogen coming together, and it emits an electron and something called a neutrino. Here's the index down here, and or a positron, sorry. And then it combines eventually to make helium. So you'll see 2 protons and 2 neutrons that come essentially from smashing together hydrogen. So if you smash hydrogen together hard enough, and when physicists talk about smashing things together hard, another way to talk about that is to have a high temperature. When you're talking about gases or nuclear process, high temperature means high energy. High energy means smashing them together violently. So smash hydrogen together violently enough, and you get helium. This is a relatively slow process, though. This entails something called the weak nuclear force, and we're going to talk about that in a subsequent lecture. So what happens in our sun? Well, in the sun, you've got a core, and this core is where it's so hot and dense enough that hydrogen can, in fact, be smashed together like that prior picture, and it emits a little bit of energy. Little bit compared to the amount of energy stored in the total mass of the hydrogen and the resulting helium. So a little bit of the mass of the 4 hydrogens that come together to make a helium nucleus, a tiny amount of that mass goes into energy. And that energy that is left over from smashing them together, so it takes a certain amount of energy to smash them together, but you actually get more energy out of it than it took to smash it together. And that's why people talk about fusion being some kind of potentially wondrous energy source for our planet. If we can figure out a way to make fusion happen without having to create a star, then we might have a way of getting what is essentially solar energy in a bottle here on Earth. But most of the bulk of our sun does not see nuclear processes happening. It's hot because of what goes on in the core, but essentially it's just a thick plasma of hydrogen and other elements that surrounds the core. And there's not a lot of interesting nuclear processes that happen beyond the core. It's just classic thermodynamics. You get some radiation trying to move through it. You get some churning. One of the interesting facts is that when energy is liberated by E equals mc squared in the core of the sun, it takes about 25,000 years for that energy in the form of light or convective currents to make its way to the surface of the star, or our sun, where it's emitted as sunlight. So the sunlight that we're basking in this morning was liberated from hydrogen atoms when our ancestors were still living in caves. So processes involving astronomical objects, even a single star, can have mind-boggling durations. And there's other things about our star here, which I'm happy to talk about if anybody has any particular questions, but I'm not going to go into the details otherwise. So what happens in different kinds of stars? Remember I was talking about those dense red stars? Those stars are so small that the churning or convective current in those stars does an excellent job of mixing the hydrogen all throughout the star into the core. So those stars are amazingly efficient at burning their hydrogen. And these stars can live for nearly 1 trillion years. These stars have enormous lifetimes, at least 100 billion years. Vastly longer than the life cycle of our sun. Our sun has convective currents around the core and nuclear processes in the core, and our sun, or a star like our sun, might live for about 10 billion years. And then for vastly larger stars, some of those large white-hot stars, there's convective currents. The temperature in the core is so hot and the pressures are so great that there's a lot of convective currents inside the core, and then you get radiative energy transfer in the shell. So what does this mean? The long and the short of it is live fast, burn hot, and leave lots of elements. So each of these processes creates some kind of higher order element from what existed before. So this creates helium out of hydrogen. Our sun creates helium out of hydrogen. And as stars age, they can then take that helium and through a relatively more complex process, create things like carbon and nitrogen and oxygen. So many of the same processes that smash together hydrogen in the center of our sun and give rise to helium also gives rise to many of the other elements we see in nature. So here's a typical life cycle of our sun, a star like our sun. Remember the protostar that we began with, that disk surrounding a baby star? It turns into a star like the sun, and then as it burns most of the hydrogen in its core, it might do that helium flash I talked about. And then it might spend a little bit of time actually burning helium as a fuel and making carbon. And it keeps getting bigger during that period because helium burns hotter, as it were, than does hydrogen. And it sloughs off the outer layers of itself. So about 10 million years it takes for a protostar to turn into a star. A star like our sun converts hydrogen to helium. It can do that for about 10 billion years. A red giant lasts, this is the same star, this is like our sun. Our sun will be a red giant after a helium flash for about 10 million years. For about 100 million years, it will burn helium, and then it will go through a fairly complex process where it creates some of the carbon and whatnot, the double shell burning, and that only lasts for about 1 million years. So compared to 10 billion years when it's just sitting there churning away, converting hydrogen into helium, when it's converting some of that helium into more complex elements, it doesn't take very much time, 1 million years. And then it begins pulsing. It burns through a layer, and that layer turns into a heavier element, which sinks to the core, and then it burns through that, so it kind of pulses a little bit over time. And that pulsation can take about 5,000 years. So now we went from something that's 10 billion years long for a physical process to a process that is fairly dynamic. It causes the star to pulse, and it only lasts for about 5,000 years. And as it pulses, it sheds some of the outer layers of gas. It sheds some of the hydrogen and helium that has constituted the outer layers of the star, and eventually it turns into something called a white dwarf. In a white dwarf star, there are no nuclear processes. It's not converting anything into anything else. But it is incredibly dense and incredibly hot, and it takes it a long time to cool down. In fact, it takes so long for a white dwarf to cool down that the white dwarfs left over from the first stars made in our universe, resulting from the Big Bang, the white dwarfs that are the oldest white dwarfs in our universe are still white hot. They're still radiating enough energy just cooling off that they're glowing white hot, even though they're not turning mass into energy. And it'll take 1 trillion or 5 trillion years for a white dwarf to cool off to become a black dwarf, just a cinder. So the whole dynamic energy releasing life cycle of a star can take longer than the age of our universe. And these processes can, as I said, can produce nitrogen, oxygen, neon, sulfur, some other advanced elements. So I talked about the life cycle of stars. Let me talk now about the deaths of stars. So gravity always wins. Gravity is always pulling things together. Lord Kelvin was right about that. He thought that it was just gravitational cooling that powered stars. Turns out it's nuclear processes. But eventually gravity will win. And some of the most beautiful objects in the universe were formed by the deaths of stars. When gravity eventually wins, it causes some rapid and incredibly dynamic processes, the results of which give rise to some of the most beautiful things we can see. So this is a burned out core of a star buried in this red bubble here. This is an infrared photograph. And these are the outer layers of that star that have been emitted into space. And as we zoom out, we see that it looks like this. It looks kind of like an eyeball or an iris of an eye. This is just the normal process of the life, or in this case, as it were, the death of a star. Here's another example. This is the same process, but they think that there was enough gas and dust left over from the star's formation near the center that it kind of acted like a girdle and choked off some of the bubbles so that they came off in each direction. So this is an hourglass shape in space. It's the same process with a star that has slightly different dynamics. And then there's another one that looks like this. This is the same kind of hourglass structure, but we see it edge on. And these are real things. We can look out into the sky with telescopes and we can see these. And we can explain them, right? They are clearly explainable as natural occurrences of nuclear and gravitational and thermodynamic processes happening in balls of gas. And yet they give rise to such complex and beautiful things. And next year, when I talk about natural selection and abiogenesis, we're going to talk about a different context in which highly complex and beautiful things can arise from very simple elements. This is perhaps the most spectacular view of one of these. Again, this is just what's called a planetary nebula, because some of those, like the first one I showed you that looked like an eye, when astronomers first discovered them, they saw these colorful disks and they thought, well, maybe those are planets. So they were called planetary nebula. But as you see, they're not always disks. In fact, here you can see that gas and dust that acts like a girdle around the star that confines the ejected outer shells of the star into these two lobes. Gorgeous things. So when you get a star that's even heavier than the sun, you get even more complex nuclear processes. And I don't have time to talk about them. I'm sorry? Okay. So you get more complex processes. So you can get iron in the core, and then you can get silicon and sulfur, oxygen, magnesium, neon, helium, carbon, hydrogen still left in the outer layers. So this is a star that must be much heavier than the sun, because gravity has to be able to become strong enough to create high enough temperatures that it can actually start causing nuclear processes on oxygen and carbon and silicon. And it ends up with iron at its core. But there's a problem once we get to iron. So remember E equals mc squared? So that means that as you are engaged in certain nuclear processes, you can liberate energy. So you can do that up until iron. Remember, it takes energy to smash atoms together. The energy essentially comes from the heat due to gravitational collapse. So gravity heats up the gas and a star and the plasma hot enough that the helium or the carbon smashes together. And when it smashes together, it releases more energy than it took to heat it up in the first place. Right? So it actually liberates a net amount of energy. But once you get to iron, that stops. Once you get to iron in a star, it takes more energy to smash iron together or to smash iron together with something else than you get as a resultant from having smashed them together. Does that make sense? Okay? So stars during their normal life cycle of being spherical balls of hot glowing plasma, during their normal life cycle, stars, even the largest stars in the universe, stop their metabolic processes when they reach iron. But when we see gold, and when we see lead, and when we see other elements on the periodic table, there's 92 naturally occurring elements, or 96 or 98, depending on whether you count the short-lived ones. But there are many atoms beyond iron. What's iron? 56, I think? Does it say? Yeah, I think iron's 56. So there's many elements. 56 to 92 leaves a lot of room for additional elements. So where do those elements come from? If they're not made by the metabolic processes of stars, how do they get here? So this talks about, for a large star, the periods of time during which it burns these different things. So it goes through each of these progressive chemical elements for a shorter duration. And I'll just let you read these. Remember I said live fast, burn hot, and leave a lot of interesting elements? Well, this is the amount of time it takes it to metabolize or process these.
For people in the back that can't read that, it goes from 7 million years for hydrogen down to silicon burns in 1 day. All different shorter time frames. That's the time that the star is actually producing that.
Right. So a big, heavy, bright blue star only lasts for 7 or 8 million years total. Not at all like the 10 billion years of our sun. So the smaller the star, the longer it lives. But it can't be too small. There's this fine balancing act. It can't be too small or it's not heavy enough to start nuclear fusion. So Jupiter is made out of the same stuff that the sun is, but Jupiter isn't big enough and heavy enough to start nuclear fusion. Jupiter does emit more energy than it receives from the sun. Anybody know why? Because it is working on the same process that Lord Kelvin talked about. It is still emitting some amount of energy from collapsing initially 4 billion years ago when the solar nebula was forming. So Jupiter is actually still a little bit hot from the gravitational collapse. It's not nearly hot enough to emit light, which is what Lord Kelvin assumed was happening with our sun, but gravitational release of energy generates heat, and it's still happening in our solar system. All right, some exotic stars. Variable stars, as stars burn through certain chemical elements, or as the convective currents inside the body of a star becomes more dynamic, you can get stars that pulse. And when they pulse, their brightness seems to change, maybe their size seems to change, and variable stars are very important in astronomy for other reasons that I won't get into. You can have supermassive stars. You can have a star that is 150, maybe 200 times the mass of our sun. You can get something called a Wolf-Rayet. That just happens to be the name of the prototypical star, the first star that was discovered that had this characteristic. This is a star that is so big and massive, it's about 20 times the mass of the sun, that it has such a strong solar wind that it's essentially blowing part of itself off. This is different than the mechanism that creates a planetary nebula, because this is a healthy metabolizing star that's burning chemical nuclear fuel, but it's so hot, releases so much energy that it blows away some of its mass. And that's actually what causes there to be an upper limit on the mass of stars. If you tried to get a star heavier than about 170 or so times the mass of the sun, the currents, the convective currents and the solar wind emanating from those would be so hot that it would prevent more mass from accruing or accumulating. Hypergiants, we talked about those, the 100-meter star compared to the baseball. Population 2 stars, which are stars that are older than the sun, that were formed at a period of time when the universe had less time to seed the cosmos with carbon and nitrogen and oxygen. So those stars, some of the oldest stars we see, are in things like globular clusters, of which this is a picture, or in our galactic core. Some of the oldest stars have low metals. Astronomers apparently flunked chemistry because they say anything that isn't hydrogen or helium is a metal. So when they talk about low metallicity stars, they're talking about stars that have mostly just hydrogen and helium, and we see those ancient stars in places in our universe. We actually have within the solar system, we have granules. These granules are carbon and silicon bits of dust, and trapped inside these bits of dust are some gases. Well, remember, I talked about how massive stars can synthesize silicon and carbon. Well, what that means is that we can expect some of these little granules of solidified carbon and silicon to have come directly as soot from ancient giant stars. So how can we further prove that that's the case? Well, if we rip one of these things apart in a very controlled manner and we look at the gases that are trapped inside them, we see things like hydrogen and helium and neon. We see an abundance of gases, and the quantity of those gases matches perfectly with the mathematical projections about what those ancient stars would be constituted of. So these granules that we can find from space are literally pieces of ancient stars. And we know that definitively. But it's granules like this that formed trillions and trillions of tons worth of material that eventually became the Earth and eventually became the Sun and Jupiter. So when we ask where did the elements on Earth come from, they came from an agglomeration of particles that were emitted as gases and dusts from a prior generation of stars. You've heard it before. We're made of star stuff. It's amazing. Every atom in your body, excepting perhaps the hydrogen, once lived in a star, especially the carbon. The carbon in your body was likely at the center of a star at some point. That's amazing. And then what happens to stars that are so big that they don't end their lives as white dwarfs? Well, they explode as a supernova. This is not a picture of a supernova. This is a picture of a star called Eta Carinae that we believe, humanity believes, scientists believe, that it is getting ready to explode as a supernova any day now. Someday between now and a few thousand years from now, this thing is going to go kablooey.
Well, it already happened, it just hasn't got there yet.
Oh, yeah, that very well could be. Because it's 7,000 light years away, in its time frame, it could have already happened. It nearly exploded in 1841. It emitted a big pulse of light. Neutron stars. So what happens when a star about, more than 7 times more massive than the sun, when it ends its life, gravity wins, and gravity wins so violently that it smashes all the elements together, and that causes explosive nuclear burning. And that explosion of energy causes a rebound for the star to blow itself apart. It still may leave a bit of a core, but most of the bulk of the sun, including all those wonderful elements, carbon and nitrogen and silicon and sulfur, etc., are blown out into space as a supernova. Also, the energy provided by the supernova is enough to generate some elements beyond iron. It doesn't liberate energy, it consumes a little bit of energy from the supernova to create those elements, but it does produce some elements beyond iron, but not gold. We're going to talk about that in just a minute. So here are the supernova nucleosynthesis. I apologize for the little bar here. So the idea is that the Big Bang was the source of hydrogen and helium and a tiny bit of lithium. Interesting story about lithium on a side note, it's really hard to get a dynamic stellar process that leaves behind lithium because lithium is a good intermediate product that's consumed. So if we ever see lithium in a star, we know that something weird is going on. And this is one of my favorite discoveries from the past couple of weeks that I learned about. There's a star that's been discovered that's a red giant star, and it's got a lot of lithium in its light spectrum. We know that it has lithium in it. But lithium shouldn't be there because stars use lithium as part of their metabolic processes and don't emit it as a byproduct. So why would we see a star with lithium in it? Well, it turns out that having a giant star that has a lot of lithium in it is completely consistent with a theory that was devised, I think, in the 60s or 70s by some theoretical physicists who said, what would happen if a star grew so big that it grew beyond a companion star that happened to be a neutron star? So if a star lived and died and a supernova and left behind something called a neutron star, and then a star that was near it grew to envelop that neutron star in its outer layers, there would be nuclear burning happening around that neutron star using lithium, or generating lithium, but the solar wind and the convective currents from the enveloping star would push that lithium out into the outer layers. Very complex process. And they were able to predict this 20 years ago, and they verified it last summer, or tentatively verified it when they found a red giant star with a lot of lithium. That's the only known way that you can get a lot of lithium in your star. Many of these other processes, there's some different nuclear processes, something called a slow process and a rapid process, S and R. And the different elements in the periodic table talk about where they come from. Nova, when matter falls onto a white dwarf and causes explosive burning, you might get just a regular nova, and novas generate these black dotted elements. Supernova generate the red dots for sure, like totally. And then the yellow dots, there's a problem with those. So there's a nuclear process called the rapid process that is thought to generate these elements with the yellow dots, including gold. This is copper, silver, and gold. Au is aurum, I think, aurum, and that's the chemical symbol and name for gold. Well, when astronomers have looked at supernova remnants and looked for some of these elements with the yellow dots, they find that there really aren't many. So even though in theory they should be generated by our processes, nature is telling us something different. Remember in my last talk I talked about how the story of the Big Bang is full of surprises. Well, this is one of the things that's surprising, is that many of these elements that should be generated during a supernova aren't found in the debris of the supernova. So the idea is that a lot of those heavier elements are trapped in the core of the neutron star that constitutes the supernova. They don't get liberated into space. So how do they get into our world? How do we get gold? How do we get silver if they're not liberated by supernovas? Well, we'll talk about that in a second. Here's another example of the end life process of a star. This is a black hole. I'm not going to talk a lot about it, except if you get something that's heavy enough, gravity ultimately wins, and there's nothing visible left over. You just get a kind of a rip in the fabric of space and time. It sounds like science fiction. One of the things that we know about the disk of gas and dust that might swirl into a black hole is that around that gas disk, we could get lithium. So this is the second place we know that lithium could come from. One is that star I talked about, and the other is if you look and you don't see a star, but you see some lithium, then it's a good indication that you've got an accretion disk around a black hole. And some stars can orbit black holes safely. Then there's this idea of a kilonova, which is a titanic supernova that doesn't result from the end of life of a single star, but rather results from two colliding neutron stars. It's very intense, it's very brief, you get a lot of gamma rays, the energy is so prolific that you don't even see much visible light, and that the only known process that could generate that is the collision of two neutron stars. And you get rapid and exotic nucleosynthesis, and this is believed to happen about once every, I believe it's 100,000 years or so in our galaxy. And here's an artist's impression of what that might look like. Now, when two neutron stars collide, a lot of the energy can go into emitting heavy neutrons, or neutrons, clumps of neutrons, and those clumps of neutrons could essentially freeze into other elements. And this is a very plausible explanation of where gold comes from. So imagine if you have a gold ring, or I have a little ball full of gold here. Imagine that all of this stuff is the leftover cinders from a neutron star. Isn't that amazing? And we know that now. And Charles Darwin didn't know that. Lord Kelvin didn't know that. But we have had verifiable scientific predictions about the life cycles of stars and the way that chemical elements are generated, such that we now know that gold comes from almost certainly, there's still some debate about it, almost certainly comes from the leftover shattered pieces of two neutron stars. Amazing. So where does the gold on Earth come from? Well, it turns out that during the time when those granules I talked about made the Earth, most of the gold and heavier elements were so dense that they sank to the core of the Earth. So we shouldn't actually see gold at the surface. And the only reason we see gold at the surface of the Earth is because it was delivered later. If you calculate how much gold should be created by the collision of two neutron stars, it's about 10 moons worth, the mass of our moon, about 10 times that. And if you talk about all the gold that's ever been mined or discovered on our planet, it's about one Olympic swimming pool's worth. So gold is rare, but whatever generated the gold on Earth likely generated about 10 moons worth of gold, and there's probably gold in some asteroids in our solar system. So the gold sank to the center of our Earth during its formation, and after that, some meteor bombardments after the Earth had cooled off and was no longer liquid and churning. Subsequent bombardments by meteors delivered the gold and silver and some of the other denser elements that we currently see today. And that is the story of gold and the lives of stars. Thank you. Join me next time when we're going to talk about why math is important for science. And it's not going to be, if you're not a big fan of math, I hope you'll still find it interesting. We're going to talk about things like imaginary numbers, etc. So I'll take some questions. Thank you very much. Yes.
Following your reasoning here about how gold got to the Earth, it would seem to be it ought to be evenly spread around the Earth, and yet it isn't. It accumulates, or at least appears, in fairly small, localized places.
Yeah, so meteor strikes were probably fairly localized. Maybe this meteor had gold in it, and other meteors that occurred during this same period of time didn't have much gold in them. Also, plate tectonics can recycle and gather together the material in the crust of the Earth without necessarily requiring that material sink down into the core of the Earth. So the different densities and geochemical processes on the Earth can cause things to come together. You know how arsenic, I don't know the exact chemical process, but arsenic has an affinity for gold, and so you can potentially accumulate gold wherever you accumulate arsenic. So there are chemical processes that can cause gold to accumulate, and different physical processes may have made the distribution uneven to begin with. Yeah, Al.
Let's go back to iron for a minute.
Yeah.
Iron seems to be a very crucial element. What is it about iron that makes it so important that you can emit more energy than you consume below iron?
Okay.
And above iron, you go the other way.
Good question. So, the nucleus of every atom is comprised of neutrons and protons. Well, protons have a positive charge, right? And if you have another nucleus of another atom, maybe it's carbon, maybe it's helium, maybe it's another iron atom, that nucleus will also have a positive charge. When you try to bring those two nuclei together, the positive charges will repel each other. And that will keep them from coming together. There's another force. I talked a little bit about the weak nuclear force. There's something called the strong nuclear force that once you get them, in a sense, close enough, the strong nuclear force, which is much stronger than the electromagnetic force, can cause them to sort of explosively collapse into each other, and that's when the energy is released. But the electromagnetic repulsion, the electrostatic repulsion between iron and other nuclei is so strong that you can't get them close enough together for that nuclear process to be effective and still release energy. It takes more energy to smash them close enough together to overcome that electrostatic repulsion. It takes more energy to do that than you get by liberating a little bit of energy when they do come together.
Yeah, there's so much information in this, at the risk of a bit more, I'll add a couple of interesting facts to
Sure.
One is that we mentioned the idea of getting nuclear fusion energy from fusion, which is what's happening in the center of the sun. But the tokamaks that you hear about is not reproducing the energy reactions that take place in the sun and stars, because using deuterium and tritium is unstable and doesn't exist in the sun. So these reactions one's trying to do in fusion reactors they're not actually reactions that take place in the center of the sun and stars. An interesting fact, I think, also is that imagine taking the cubic meter of the center of the sun, okay? This sort of size, and it weighs 15 tons of plasma. 15 tons, it's 15 times more dense than water, and it's 150 million degrees. So the net energy output from that cubic meter is less than 100 watts. Less than 100 watts. But there's a hell of a lot of sun. That's how the sun gets so much. But, of course, if you had that cubic meter, it would immediately cool down. But if you could keep it at that temperature and pressure, the net energy output is only 100 watts. So that's a sobering fact, I think.
Yeah, thank you, Mike. And that explains why we're trying to do something a little different for the terrestrial nuclear process, or one of the reasons. Other questions? Yes?
I'm worried about the helium flash that our sun may go through. When's that going to happen?
What time is it?
You've heard of hot flashes.
Yeah. It's going to be at least 4 billion years from now. So we've got a little bit of time. Thank you for helping me clarify that. Our sun is about in the middle of its 10 billion year steady state burning process. So it's got 4 or 5 billion years left over as far as we know. And eventually it'll get large in that red giant stage. It'll potentially get large enough that it gets to the orbit of Earth. But at that point, the density will be about 1/1,000,000th of the density of Earth's atmosphere. But it's still going to be hot enough to cause problems. Yeah.
Yeah. I'm wondering if you can predict ahead, like when there's certain things that happen in the sun that will affect our smartphones and our communication, and that would be just catastrophic.
Yeah, that's a great question. So one of the things, I didn't get into that very much, talking about the actual dynamic processes of a steady state star, but one of them is solar flares. And solar flares emit a lot of charged ions out into space. And we had a near miss, what was it, about 12 years ago, from one that, had it actually been directed at Earth, it wouldn't have fried us, literally. It wouldn't have caused a temperature increase, but the charged particles might have certainly wreaked havoc with some of our electrical grids and satellites and whatnot. In terms of predicting those, to my knowledge, scientists don't yet have the capability to predict when a large flare will happen. They tend to happen with the same periodicity as the solar sunspot cycle. And what is that, like a 12-year cycle or 13-year cycle? But the sun could emit a large flare at any point. And as far as I know, we don't have the knowledge or the detailed models to be able to talk about when that happens. Yeah.
I seem to recall having heard somewhere that they have or are launching some satellites that might give us enough time if a coronal mass ejection happens to power down satellites and power plants to prevent the entire grid from turning into a molten slag heap, which would be kind of a bad thing.
Yeah, one thing about solar flares is that the light from a solar flare will reach us 9 minutes after it happens, but the charged particles might arrive a few hours or even a day later, so we might have a little bit of time to at least prepare. Yes, ma'am.
Most of what you talked about today, it seemed to me it was things standing alone, except for the collision. Can you talk a little bit more about the collision of the stars?
Let's see. What can I say?
I'm not a scientific person,
Sure.
but I'm just wondering, how does that happen?
So when Newton came up with his theory of gravity, he showed that there were many orbital possibilities for things that are gravitationally interacting with one another. One is a circle. That's very rare. You can also have an eclipse, or an ellipse, I'm sorry. You can have a hyperbola or a parabola. And occasionally, it might be that because of some other third object involved in that gravitational dynamic that you shift one. So if it's something on a highly elliptical orbit around another thing, and it shifts a little bit, then maybe instead of just brushing by a thing, it actually collides with it. So if you perturb the orbit some way, and there are many ways that could happen. It could even be the radiation from two things that are interacting. If you perturb that orbit in just the right way, it's going to be rare, but it will still cause their trajectories to actually cause them to collide. Yeah.
A lot of rocky planets like the Earth have a hot core where something. Is that the result of some of those higher elements that have sunk to the center and are doing nuclear fission?
So no, but you're close. Oh yes, fission. Actually, you are right. So it is fission. Yeah, so there is uranium and thorium and other things at the core of our Earth, and part of the reason that the core of the Earth is hot is because of gravitational collapse and leftover heat from that. But a good amount of the heat in the core of the Earth comes from the decay of radioactive isotopes. So most of the uranium in Earth is at the core, fortunately. But that's nuclear fission, not fusion. It's a much different process than happens in stars.
Just briefly, what causes the poles to change, and is that going to happen sometime?
Oh, the magnetic poles of the Earth?
Yeah, the magnetic poles.
Yeah, convective currents in the core. So anytime you have something hot that's viscous, it'll flow. And those set up things called convective currents. And current thinking is that those currents might chaotically rearrange themselves occasionally. And it's those currents of moving charged material that give rise to the Earth's magnetic field. So we know that it has happened, and we are actually in the middle of what is believed to be a magnetic polar flip. Well, not necessarily the middle. We are in some stage of a magnetic polar reversal right now. It's pretty certain. The magnetic field, the North Pole is drawing a magnet less strongly than it did 500 years ago. What does that mean? It means that at some point, the North Magnetic Pole will become the South Magnetic Pole. And during that process, it's an open question about whether it will happen like this or whether it will go away and then come back. If it goes away, that might open a window for more charged particles emitted from the sun and cosmic rays to have an impact on Earth. And that could be dangerous. It's not likely to be absolutely catastrophic, but it could be dangerous. It may be that wearing hats becomes required for a few generations. I don't know the specifics about it, but a magnetic polarity flip in the Earth could be somewhat dangerous. Yeah.
Wasn't there some theory about that being the cause of the Cambrian explosion? The extra energy hitting the Earth from the...
Oh, really? I'm not aware of that. Sounds plausible, perhaps, causing more mutations. Yeah.
There was a lot of discussion about extra oxygen causing the Cambrian explosion, and just more nutrients, more energy.
Yeah.
Available.
More metabolic energy rather than cosmic energy.
Right.
All right, well, I'm happy to take more questions if you want to stay. Otherwise, we're probably going to go out to lunch and come back and at 1 o'clock and play some board games. Thank you very much again.